Hello and welcome everyone. Last month, the excellent YouTube channel Numberphile aired a Ben Sparks episode about the dice game Pig. It was, as usual, entertaining and well produced. Pig is a simple game, but even simple games can present challenges and exhibit interesting patterns. Despite its simplicity, or maybe because of it, Pig is popular in both math and computer science departments, and Pig-like games have been analyzed many times before. So today I would like to take a look at the gap between what Ben presented and the technical details you might expect to find in an academic paper. And by gap, I specifically mean how you go about solving a game like Pig, where solving means finding the optimal game strategy, the best move in any conceivable Pig game. And after we have this optimal strategy in hand, we can examine the performance of human strategies. And it turns out that Pig is quite unique, because there is, spoiler spoiler, a simple Pig strategy which is extremely close to optimal. So, even if you skip most of this video, from now on you will play Pig like a world champion. Let's get going then. Pig is a simple game, but not simple enough, so I'm going to start with something even simpler. Hawaii 5-3-0. Hawaii 5-3-0 is also a dice game, where players roll the dice, accumulate points, and the first to 11 wins. There are two dice in Hawaii 5-3-0, Dano and Steve. All the faces on the Dano die are 3, so basically Dano always books a 3. On the Steve die, 3 of the faces are blank and 3 are 5, so you have a 50-50 chance of scoring either 5 points or 0 points. Every turn a player picks one of the dice, rolls it, and adds the points to the running total. Here is how a game might go. I Steve, but unlucky and get 0 points. You Dano and get 3 points. I Steve again, but get 5 points this time. You Dano again. The score now is 6-5. I Dano get to 8 points, and you Steve get lucky and win the game. Easy peasy, right? A trivial and pointless game. Prove it to me then. Pause the video now and figure out by yourself what is the best first move and what is the best response or responses are, and so on. You can do it, but it's not as easy as it looks. In any case, here or with any other puzzle, it's worth trying. You will learn far more than by just listening to me. You will find it easier to understand what I'm about to say, and you will certainly have more fun. You can pause right here. Welcome back. Let's get rolling again. Hawaii 5-3-0 is a race for points, so you better get the maximum number of points at each turn, right? If I Dano, I get 3 points. If I Steve, I get 0 points half of the time and 5 points half of the time. So on average, I get 2.5 points. In most civilized universes, 3 is bigger than 2.5, so I should Dano every time. So a game would look like I Dano, you Dano, I Dano, you Dano, I Dano, you Dano, and I Dano and win the game. Quite boring, but it's okay as long as I get to start every time. However, if this was a real game, and especially if there was some money on the line, I'm pretty sure that when you go to 6-9 you would stop and think. If I Dano, I'm going to lose for sure. I'm throwing the game away. Do I have a better choice? Of course I do. I can Steve. Half of the time I get 0 points, but that's okay. I was going to lose anyway with the Dano. On the other hand, half of the time I get 5 points and win the game. I got from 0% chance of winning to 50%, from nothing to even. And this is the main lesson of Hawaii 5-3-0. In a game, we don't try to maximize expectations, but winning chances. Sometimes when we are behind, we need to make moves that have low expectation, but higher winning chances. This simple truth applies in each and every position. Let's take a look at 6-6. We now know that after I Dano, I have 50% chance of winning, because you Steve and win half of the time, and I win when you don't, which is also half of the time, 50%. But if I Steve at 6-6, I immediately win half of the time by rolling a 5. And when I roll a 0, the score remains 6-6, and you get to roll. So think about it for a second. If I Steve, I immediately have 50%, and in the other 50%, I might win some, lose some, it doesn't matter. I have at least 50%. And this is the second lesson from Hawaii 530. If in move A, I have 50%, and in move B, I have at least 50%, I can always prefer move B over move A. This might sound like a trivial observation, but it is a concept behind a complex-looking algorithm called alpha-beta pruning. Many complex algorithms are just a simple idea surrounded by a cloud of confusing details. However, knowing the right move doesn't mean we know the winning probability. For that, we will use another simple but powerful trick. Let us call the winning probability at 6-6 P. We know that by steving, P equals 1/2 plus something. This something comes from the times I rolled a blank and you got to roll at 6-6. You, obviously, listened very carefully to what I said and steve as well and win with probability P. So I win with probability 1 minus P. So now we can complete this simple equation. P equals 1/2 times 1, 1 for the certain wins, plus 1/2 times 1 minus P for the times I rolled a blank. You can solve this equation in your sleep and get P equals 2/3. To summarize, if I dano, I win half of the time. If I steve, I win 2/3 of the time. So I should steve. Let's take another step back and see what happens at 3-6. But this time, let's do it in an orderly, formal fashion. Let's start naming things like true professionals. Let's call the winning probability in this case P subscript 3:6. This is what mathematicians do. They pick the most boring descriptive names. Boring names means less confusion. Now, P36 equals what? Like before, we can either dano or steve, and we should pick the better move, the move with the higher winning probability. So let's invent more names, the more the merrier. Let D36 be the winning probability when we dano, and S36 the winning probability when we steve. So formally, P36 equals the maximum of D36 and S36. The maximum function is like any other function. Plus adds numbers, multiplies them, and max picks the largest, which is what we want, the winning probability associated with a better move. We now need to go and figure out D36 and S36. D36 first. If you dano, the score will be 6-6 with me on roll. My win probability is P66. See how those boring names help? And as always, you win when you don't lose. So your win probability, D36, is 1 minus P66. When you steve, there are two options. Either you get 0 points, and then your win probability is 1 minus P63, or you get 5 points, and your win probability is 1 minus P68. So, S36 equals 1/2 of 1 minus P63 plus 1/2 1 minus P68. And we actually know those values. P66 is 2/3. P63 is easy because the player on roll can dano twice and the opponent can get at most to 8. So it's a sure win. P63 equals 1. P68 is new, but a moment reflection will show that it's the same as 6-9. The player on roll must steve and wins half of the time. So P68 is a half. Putting it all together, D36 is 1/3, S36 is 1/4, so P36, the maximum of those, is 1/3. So the best move is to dano, which wins 1 times out of 3. Let's forget the numbers for a second and look back. This is how you tackle a new problem. You pick the easiest non-trivial part and you work your way backwards. We took the game, the rules, the mechanics, the dice, the faces on the dice, and worked out the best move for some of the positions. And to do that, we computed the winning probabilities of some of the positions, because this is what the best move in a dice game means, the move giving the highest winning probability. And we gradually distilled the process and expressed our knowledge of the game in another language, so to speak, in math speak. The equations on the screen are math speak. They now stand on their own. Any native speaker of math speak can understand them unambiguously, even those who know nothing about Hawaii 530. We eliminated thinking and reasoning. And not only that, even generating the equations themselves requires no thought. We can now generate this set of equations for any score mechanically, without thinking. If you want, say, the equations for the score 0-0, you just plug in the numbers, like so. And all those equations together are what's needed to solve the game. If we can find values which simultaneously satisfy all those equations, we have solved the game. We will know the best move in any situation and can play the game perfectly. So, how are we going to find those special values which simultaneously satisfy all those equations? Hawaii 530 is so small, we could do it by hand. But for anything bigger, we would need help. And MathSpeak is a significant step towards getting this help. With MathSpeak, we can delegate the rest of the process to a non-thinking agent, an entity which understands only a variant of MathSpeak and requires precise instructions. Edit the computer. All we need to do is translate MathSpeak into Computerize. And that's a piece of cake, because at this level, the two are very close. Here's how the equations look in my favorite dialect, Python. Don't worry if you don't know Python or any other computer language. The similarity is obvious to the eye. What might be less obvious is that the two are fundamentally different. The math equations express the relation between the various win probabilities, and Computerize is about computation. What you see on the right are statements which define computation. The name P_6_6 is but a box which contains a number, and the first statement says take the number from the box, let's say it was 1/3, compute the expression 1 minus 1/3, and place the result 2/3 into the box named D_3_6. And those statements, just those statements, will do the job. It's magic. Look. Let's say I don't know to solve the first equation that we encountered. P equals 1/2 plus 1/2 times 1 minus P. So I pick a number, say 1/2, and see if the shoe fits. No, the right hand side is 3/4. I'm too dim to solve even this simple equation, so obviously I'm not allowed to do anything smart. So I try again with 3/4. No, this time I got 5/8 or 0.625. So I feed it again and get 11 to 16 or 0.6875, and so on and so on. As you can see, the difference between successive values gets smaller and smaller until eventually it gets almost to 0 and the value converges to the solution, 2/3. Now, I use a simple-minded technique again and again. It is a well-known technique known as fixed point iteration, and it still feels like magic. I know it has to do with the fact that the equations are continuous and piecewise linear, and it's not guaranteed to work, etc., etc. But it works surprisingly well with games. We got lucky, and all we have to do is recompute and assign all the equations over and over again until the system converges. All we needed to do is figure out the equations, which is not hard, and off we go. And with the tiny Hawaii 530, we can even chart the optimal game strategy as a graph. Each node in the graph is a particular Hawaii 530 score, and the green-red shows the win-lose probability for the player on roll. So you can see from the graph, from the track going from the bottom middle to the left, that one sequence of optimal play might be Dano, 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 and at 6-6, both players steve to get a win. But you can also start by steving. This 2 gives the first player 2-to-1 odds. I put this graph here mainly to illustrate that even the simplest of games can hide some complexity. And all this complexity must be taken into account when establishing optimal play. We must compute the probabilities for all scores, trivial or not, and establish the optimal play at each junction. We must, for example, compute the whole subgraph going to the right from the score 0-3 to make sure that Dano is better than Steve. Okay, let's go the whole hog. In Pig, players accumulate points by rolling a standard 6-sided die. Player gets 2 points from rolling a 2, 3 from rolling a 3, but lose both the turn and the stash when rolling a 1. Each turn is a series of stop-and-go decisions. The player may at any time bank the current total and pass a dice, or roll again. It's all about knowing when to stop and cash your winnings, just like Bitcoin or Canadian cannabis shares. Solving Pig after a Wi-Fi 3.0 is a breeze. We just write the equations and set Eddie in motion. Let's name stuff as usual. Let P100-100 be the win probability of the player on roll in the starting position. P is for probability or Pig, take your pick, and the 200s are the away number, the number of points each player needs to win. There are 6 possible outcomes after the roll. If the player rolls a 1, with probability 1/6, her turn ends, and the die passes to the opponent. In that case, she wins 1 minus P100-100 of the time, just like when a player in Hawaii 5-3-0 rolled a blank. Otherwise, the player wins with probability P100-100 when rolling a 2, P100-3-100 when rolling a 3, and so on. The number in the middle stands for the number of points accumulated so far. Now, we need to write the equation for each of the new terms. Let's do P100-6-100, the win probability after the first player rolled a 6. Here, there are 7 possible cases. The player can bank the 6 points or keep rolling and get 1 to 6. When banking, her win probability is 1 minus P194. That is the probability when the opponent trailing 0 to 6 doesn't win. When the player keeps on rolling, it's similar to what we had. The 1 keeps the score and puts the opponent on roll, and 2 to 6 accumulate more points. It's very confusing at this pace, I know, but don't worry. I only wanted to show that Pig equations are very similar to Hawaii equations, just slightly longer. There is, however, one big practical difference. There are about 500,000 of those critters, 10,000 times more than Hawaii. But again, no worries. Computers got so fast, 500,000 is a very reasonable number. I can solve Pig on my laptop in less than 5 minutes, using nothing fancier than pure Python. And the question is, what now? You can print the game graph on 10,000 pages and lay them down on 3 tennis courts, but don't expect to learn much. We need to distill those values into something comprehensible. A chart of stop values, for instance. Each score has a stop value. The first total the player should bank and pass the dice. At the start, 100 away to 100 away, the stop value is 21. The player should roll on with 20 or less and bank 21 points. But at the 100 away 79 away, that is, after your opponent banked 21, your stop value is 23. And if your opponent has 40 points to your 0, 100 to 60 away, your stop value is 26, and so on. The figure in front of you shows those stop values for all possible scores. The bottom right is the game start, 100 away to 100 away, and the top left is the end, 2 away to 2 away. The figure aggregates scores into ranges to reduce the visual clutter. It also shows the no-stop scores in green. At a no-stop score, you go the whole hog. You roll until you either win or bust. Now, I don't know about you two, Varish, but I find this figure fascinating. I know it's not the Mandelbrot fractal, but they come from the same stock. Both figures arise from a simple set of rules and reveal an unexpected chaotic picture. And Pig stops are useful knowledge, both specific and general. For example, A. If you are 22 away or less, go for win or bust, regardless of opponent's score. B. If your opponent is 16 away or less, also go for a win or bust. C. The overall structure is as expected. You need to be more aggressive when trailing and more conservative when leading. When about even, the stop value is in the low 20s. However, there is no easy way to remember by how much to adjust. Only a computer can play perfectly. Stop points paint a nice picture, but fail to tell us what we really want to know. How much of this information is needed to play well? And the surprising answer is none at all. The most basic strategy of using a global cutoff of 25 works amazingly well. And by amazing, I mean only 14 ELO rating points separates Eddie, our perfect player, and Cat25. 14 ELO points is the rating difference between Ian Nepomniachtchi and Fabiano Caruana. 14 ELO points mean the stronger player is expected to win about 52% of the time. Think what it means for Pig. It's like Aragorn by himself storming Mount Doom, which is protected by 500,000 orcs, and coming back to tell the tale 48% of the time. And how do I know it's exactly 14 ELO points? Same old math. For any two strategies A and B, we can compute the rating difference between A and B in the same way we computed the optimal strategy. We need twice as many equations, one for A's probability of winning on roll in position P, and one for B's win probability in that same position P. I won't go through the details because by now you can easily do it yourself, and the judges had plenty of other material to skip over. Let's instead look at the skill rating of other cutoff strategies, from Cat 16 to Cat 28. And voila, Pig irregularities spring right back. Cat 24 and 25 are separated by one measly rating point, 0.1% in win probability, but Cat 23 rating is 29 ELO points, 2% less winning chances than Cat 24. And it's worse than Cat 26, 27, 19 and 20. And this is only the tip of the Titanic. If we change Pig to Pig 99, the first to 99 wins. Suddenly Cat 24 is 2 ELO points better than Cat 25. And with Pig 95, Cat 23 is the best overall. Look at this plot of skill rating of Cat 18 to 28 for any Pig game from 2 to 100. Each cutoff strategy up to Cat 42 is best at some Pig target score. Pig is a simple game with chaotic behavior, just like other simple rule systems made from a large number of small parts. Any small change in the rules will change the optimal strategy, and quite often which heuristic strategy is best. We got used to finding chaos in nature, but might be surprised to find it in games. We shouldn't. It's not the medium, it's the underlying math which drives those systems in similar ways. But despite the chaos, this Pig is toast. 25 is my only move. Now it's your move. Pick any Pig or Hawaii variant you like and see what chaos you can come up with. Happy hunting.